It's really quite strange standing up here talking about a piece of innovation that was probably designed around 40 to 45 years ago. So this really shows basically when the innovation starts, it continues and continues for many a year. So basically what we're looking at here is the latest tamping machine, which has now become sort of the predominant machine on the UK market. And it's an 09 4x4 4S, dynamic. And the word dynamic means it's not one machine, it's two machines. It's a tamping machine and a DTS. You can buy DTSs, which work independently, but in this mode, because it's an 09 series machine, the machine is what's called a continuous action tamping. The main frame never stops. It's just a section of the frame which stops and allows us to tamp. So my presentation is basically around this. So these are the different types of machines within the UK. We don't have so many on the top left-hand side, but we have around about 10 09 3X dynamics in this country, maybe more. We have around 10 09 4x4 4S machines, and we have two what's called combination tampers or consolidation machines which work within the high output system. So you can see we have quite a number of DTS units or DTS systems working around the machine, working around the country. But as I said to you before, I want to really look at basically is the 09 4x4 4S dynamic, and it has lots of tools in its nice shiny toolbox which we can utilize to basically improve the quality of our tracks. So probably you will find, as I said, it's over 40 years since we actually started building these machines. There have been numerous pages, and probably you will find it's probably the machine that has basically been tested, trialed, looked at. Lots of conversations have talked about this about DTSs. There has been significant investment on trials and investigations of how the DTS works. So you can see there's much work has been done on the DTS already, but we continue to invest into it. So what does the DTS do and what's its benefits? So basically the first part is the uniform distribution of dynamic forces in a track structure. This sounds quite complicated. Basically what we're saying is we are basically allowing the forces to go through the rails, through the sleepers, and use the ballast to transfer their load into the foundations. So what we're trying to do here is to make sure we have lots of paths for them forces to travel through to the foundations. The next one is to increase the lateral resistance and longitudinal resistance of the track. Unfortunately, during the tamping process, we actually sort of lose a considerable amount of our lateral resistance and longitudinal resistance. So this machine tries to put back some of that. And the last bit is to increase the intervals between tamping. Okay? And we'll explain how that actually happens. So there's been numerous reports, and this is one of the latest ones, is looking at the lateral resistance of the machine, or the track, after tamping. Unfortunately, when we start tamping, or after we tamping, we can lose up to around 50% of the lateral resistance of the track. And this can be a problem, especially in hot weather, where we get buckling, problems with that, and especially nowadays with global warming, it's going to start hitting us a bit more. So this is just showing us basically how much force was needed to move a particular sleeper. And basically what happens is they unclip the sleeper from the rail and they measure how much force they need to move it approximately 2 centimeters. Okay? So if we do that with a piece of, with a sleeper which has not been DTS'd after tamping, we can see it's a lot lower resistance to moving. If we then DTS it, we can see that it increases it. So this allows us basically to tamp in hotter weather and to be a little bit more comfortable that the track is not going to move after tamping. So where can we use this DTS system? So basically we can use it for renewals and maintenance, okay? And we can use it in both plain line and S&C. We've used the DTS quite considerably in this country, especially in the high output system in renewals, and to some success. And we normally use this in the layer method. So basically we build up layers of stabilization. So we will layer maybe 100 millimeters of ballast, DTS it, another 100 millimeters, DTS it, and then another 100 millimeters and DTS it, and then we have our level of ballast. But we rarely use it in this country nowadays for maintenance, after maintenance. So we have lots of different machines, and this is quite a difficult slide really, but they all have different parameters, different things we can change with the DTS, okay? And you'll see later on where we get these values from. So how does it work? Well, basically, it's an eccentric shaft what rotates, and this generates a vibration, and this vibration is laterally, okay? So we vibrate the track at a specific frequency laterally, and we press down. So some people say it's like rubbing the track in the ground. It's a little bit more complicated at that. Is what we're trying to achieve is basically what the trains do. And basically, if we look at 100,000 tons of traffic, this is what the DTS does. But what we want to do is settle the track in such a way that we don't damage the ballast and we maintain the quality after the tamping machine. So we have now two types of DTS. We have what's called a fixed eccentric weight, and we have a system called what's called imbalance. This is where we're able to adjust the eccentric weight. We can adjust the eccentric weight basically from basically a balanced shaft, so there is no vibration at all, to absolutely 100%, so we get the maximum impact from the machine. So this leads us really up to using the imbalance system on switches and crossings, where we have obstructions where the machine has to stop. So basically to get over an obstruction, with the imbalance system, basically the vibration stops immediately, okay? The imbalanced weight, the eccentric shaft becomes balanced immediately. The problem with the fixed system is it needs time to rotate round and slow down. So we get different frequencies, different impact forces. So on the later machines now we use this imbalance system. So this is a closer look at the imbalance system, and this is the actual eccentric shaft you can see, and the brass colored thing is actually the eccentric weight. And this eccentric weight is moved in and out. And it's quite amazing. The movement of this eccentric mass is only 17 millimeters from balance to maximum imbalance. So it's very small. And we control this quite sophisticated with sensors to ensure that it's when we tell it to do, say, 50% imbalance, it is 50% imbalance. So we can always control what's called the impact force. And we monitor that. And if there is an error with this system, we immediately get a message on the touchscreens for the operator. So what are the variables? There are quite a considerable number, and this is why there's been lots and lots of studies about DTSing. So first of all, we got some variables what the machine can introduce. And one of them is frequency. We can vary the frequency on some machines from 0 to 40 hertz, but we don't really want to work around 0. We want to work above what's called the natural resonance of the track, which is normally around about 21 hertz. And we also want to use a frequency where we're just before that liquefaction. When we vibrate something, or stones, we can get them, if we use a specific frequency, we can get them to become like a liquid, but we don't want them to be there. We want them to be just before there. And we find them frequencies are around, depending on the track, are between 27 and 33 hertz, okay? And what that allows us to do is to move the ballast around without damaging it, or crushing it, or knocking the points off the ballast, okay? So the next variables we can have with our control system is basically the imbalance system, basically the amplitude of what we're going to apply, the force as part of the force. And this is together with the frequency. So in this instance, if you look at the orange square, these are the areas where we can control them automatically. So basically, we can control the imbalance automatically with the system, and we can also, in the next one, is the vertical load. So this is the load we push down when we start shaking the track left and right. But other variables are the variables of the machine. We have different machines. We have machines which tamp 4 sleepers. We have machines that tamp 2 sleepers. So the speed will vary. So this is a variation, and we'll look later on what them variations do to the DTS and their impact onto the track. But we also have to think about basically the track. There are an infinite number of variables in the track, and you can see here we have the basically like ballast type. Is it granite? Is it limestone? Size of it, the depth of it, the condition, is it fouled? These all affect what happens with the DTS. And then there's the components of the thing, of the track. The sleepers, the shape, and what's quite interesting is the shape of the sleeper directly affects how the frequency is transposed through the track. And also the weight of the system. So you can see there's quite a considerable number of variations here. So the variables we can control with our machine, obviously we can't control some of the things in the track, is basically these, is frequency, vertical load, eccentric load, that's the imbalance system, and the speed of the machine. And you can see the two things that really, really make a difference is the frequency and the eccentric load. On the old DTSs, we could only control the frequency. But on the new DTSs, we can control the eccentric load. So basically, we can keep the frequency where we really need it and keep it stable. And we can control the DTS basically with the eccentric load. So what is actually happening with this frequency and eccentric load? Well, this is what is giving us the force, what we call the impact force. If you want to think about it, it's the force that is moving it left and right. Okay, so we can control that infinitely with this system. And this is looking at some of the forces relevant to the position of basically where the imbalance system is and the actual frequency. And their loads are quite high. If you want to look at, if we give it 100% and we give a frequency of 42 hertz, we have an impact load of over 200 kilonewtons per unit, which is quite large. And people will go, oh, that's a lot of weight, that's a lot of force. But if you've got to remember what we're applying it to. The DTS units are 2 tons, and the track could be, what, 26, 28 tons, if we take into consideration the sleepers, the ballast, and so on. So with this DTS now, we can control and understand the impact force which has been applied to your track. So with this system, when we want to use it in a maintenance mode, we can control the variables to ensure that the quality of the track is as nearly as good as when the tamping machine went past it. Because as the tamping machine goes past it and we use the DTS, there is going to be some settlement, and this is called this initial settlement. So we can control this by 2 ways. One is by vertical load, and the other one is called by imbalance. Vertical load gives us a couple of options. Basically, we can just press down on both sides at the same pressures, but we can also alter the pressures, but on the left-hand side and the right-hand side. So that allows us basically to control the cross level with the DTS. The next is basically the imbalance system. This affects the whole, both left-hand rail and right-hand rail. And we're able to apply, you'll see later, an automatic lowering mode. So basically we can dictate how much we want to settle the track. And then we have what's called an automatic speed mode, where we can vary how the DTS works depending on speed. So this is just basically looking at a vertical load system, and this is actually what actually happens. And the vertical load can vary, depending on both DTSs, from around 40 to 240 kilonewtons. Okay, I hear a lot of things about 30 bar and 40 bar, but this is dependent on the cylinders on the DTS unit and what we actually use. So in this instance, we call constant vertical load. This is where we apply a constant load and basically normally a constant imbalance system. And normally this is used for renewal systems, where we want to use the maximum impact forces so we get the maximum consolidation of the track. The next mode we have is a method where we want to control the top of the track. The problem is when we use the DTS, we may get some uneven settlement. Okay, so that may affect the top of the track after the DTS has gone over. So what we're able to do with this system, we have a sophisticated measuring system which looks at basically like a tamping machine's measuring system. It looks at the top and basically then adjusts the vertical force to allow for variations in the track. So if there's a hump in the track or high spot, it basically increases the pressure, and if it's a low spot, it decreases the pressure. So we can vary them. Then we have different other modes to allow us to work on, say, basically high canted track. And this method basically uses a vertical load, which is constant, what we call on the low rail of the track, and then we vary the high rail pressure depending on the cross-level errors. So basically we use our ALC system to say this is the target cross-level, and then the machine compares that to what's there, and then it will adjust the vertical load to control that, so we maintain that cross level which we've just put in using the tamping machine. So imbalance. So here, this is where we're able to alter the impact loads of the system, and this has the most effect. And normally we can set a specific value for impact loads. So normal impact, we set the imbalance normally between 80 and 85%. But we can change that. If we've got areas where we're a little concerned of components around the track, we can lower that impact force. Obviously, it alters the effectiveness of the DTS, but we still get some of that goodness out of the DTS. So normally we use the standard mode, or this constant mode, is when we're doing renewals. Then we have an automatic mode. And this allows us to dictate how much settlement we want in the track. So we can actually ask it to settle the track at 5 millimeters. And you might say, why is that? A lot of countries use the DTS and they understand that if they get 5 millimeter settlement and they've lifted the track X amount, say 20 millimeters, they understand the track has settled in the right place and we're getting good quality and we're getting higher resistance to lateral displacement. So this allows them, using the impact forces or the amplitude of the thing, to control the DTS, how it functions. Okay? So it's a little bit more sophisticated than that, because if someone says, I want 20 mil of settlement, that means the system will go into saturation. But the problem is we still have to take note of what the top of the track is. And we don't want to just pound the track down and have an undulating track. So this system basically backs off the imbalance systems. If it senses that it's been at 100% for too long, it basically says, okay, there's something wrong here. I don't think we should be doing this. We're not getting a good top. I will back it back. So it backs it back 20%, and then it will try again to achieve that pressure. And what it's trying to do is maintain a smooth top after the track. This is looking at some of the settlements which we get basically after tamping, the amount of lift and basically what sort of initial settlement it is. And this is one of the byproducts, unfortunately, of tamping. When we lift the track and we tamp the track, unfortunately, over a number of tonnage of traffic, it will settle. And it's this initial settlement which we are trying to control. As you can see, it is the greatest gradient. And what we want to do is control that with as much degree as possible. Okay. We also said these machines basically are used for switch and crossings and using DTS systems. Unfortunately, when we go through DTS, through switch and crossings, we have to slow the machine down. And this means we alter the effectiveness of the DTS. So in this mode, we're able to adjust the imbalance system so we get an even, basically, impact forces throughout the DTS, throughout the switch and crossings. There are some additional forces, but these are normally used to basically clamp the DTS unit to the track. So we have some roller clamps which actually clamp onto the rail, and actually the wheels press outwards. And this is so we can transfer all those dynamic forces from the DTS into the track. So trial-wise, so a gentleman called Graham Penfold, maybe some of you will know him, he works on the Worcester region, and basically he's taken it on himself basically to use the DTS in basically the maintenance modes. And what he's doing is he's creating a register, and he's looking at how he uses the DTS in different modes. So on high canted track, he will use the specific method for, say, for working on high canted track. So we have a fixed down pressure on the low rail and basically a variable pressure on the high rail. And he looks at all these different methods of operation. So basically for S&C and plain line. And he's logging all the different ways, all the different applications, what he's used, if there's any structures there or earthworks, and so on. And then he's looking at basically what's happening to his track. Because we've said to him, yes, it should extend the life of your track or your intervals between maintenance. So basically, these are the early results of it. And of course, unfortunately, this has only been going on for the last 6 months or so. So if we look at the end of the graph, you can actually see the quality of the track. So this is the first bit is basically the high canted track. And we're just looking at basically the gradient at where the track deteriorates and how long we can prolong that. The second one is quite interesting. Basically, he gave me this yesterday. He had a piece of track which had lots of wet beds in, and they did some rehabilitation work on it, some remedial work on it. And normally, he said to me, normally they would use stone blowers here in this piece of track. But he said he decided to use the tamping machine. So he's brought the tamping machine and with the DTS, and they DTS'd it straight away after they tamped it, when they did the remedial work. And basically they've been back and DTS'd it again. And he's quite impressed at the moment of how low or how good the quality of the track is after this. But of course, it's all it's still very early in the trials. So how do we know the DTS is doing what it's doing? So we have different measurement systems on the machine. One is we've talked about a little bit before, but this one looks at the amount of settlement that's being applied to the track. So we have a sophisticated measuring system that looks after that. We also have a system which actually tries to calculate the resistance to lateral displacement. And this is based on what's called the 07 method, where we apply a pressure of 100 kilonewtons onto the sleeper, and we try and move the sleeper 2 millimeters and see how much force is needed for it. So this is on the computer, and this goes off to what's called the DRP computer and tells us what's going on. And the last thing is basically on all these machines, they have a recorder that looks at the track afterwards. And it looks at the geometrical effect on it. So always after the DTS, we can see what the quality of the track is afterwards, okay? Which is really important because this is telling us how well the DTS is working and have we consolidated the track. So with all these tools and things on that, we can utilize additional tools with the DTS system. And one of the things that has always cropped up, especially with ALCs and things, is the use of what's called design overlift, where we overlift the track more than it needs to be because we understand it's going to settle. So within the system itself, or in the machine itself, without using the ALC, the DTS system itself has the ability to increase the lift itself. It will do it by a percentage, and it takes that percentage from an empiric curve. So it looks at what lift you are, decides what it is, and then you can add from 0 to 100% on there. So we can create an overlift, so when the DTS goes over, we settle the track a little more, and we can see we get a better quality track. But we also have different other overlift systems in our arsenal of equipment. And basically, these are in with the WinALC and ALC. And this is where we can use a percentage overlift. And we can also use the system which was designed by BR many years ago, where they looked at settlement and looking at settlement curves and how much overlift you need to correct the track. And that's in the WinALC. But we also have another system which is in the Smart ALC, which is a new sort of way of looking at overlift, which is where we look at the actual mean. We create a mean point for the lift, and then we look at the lifts which are higher than the means, and that's where we apply the design overlift. Okay? So you can see there are many tools in the 09 3X arsenal to improve the track quality. So basically what I want to show you next is a little video which really sort of sums all that together and basically reviews what I've talked about.
Thanks, Chris.